Good morning, Keys Pre-Calculus. We are going to work on the last half of section 8.1 in this video. We're just continuing what we did in class. In class, we defined what a sequence is. We looked at several, including recursive sequences. And then at the very end, we looked at a special important sequence called factorial. And I'm going to redefine what that is here and then move on. If n, the number n is a positive integer, n factorial, denoted n with an exclamation point after it, is defined as 1 times 2 times 3 times 4 all the way to n. But we also showed the term before n, which is n minus 1. Remember, every term is one less than the term before it. Or one more than the term before it. Sorry, I said that backwards. You can write your factorials backwards. In fact, usually that's how I do it, and that's how we're going to do it in class because it makes more sense to factor and to eliminate common factors to do it that way. I'll show you in an example in a moment. Let's look at example 5. It says, write the first 5 terms of this sequence given by a sub n equals 2 raised to the n power divided by n factorial. Begin with n equals 0. So instead of saying a sub 1, we're going to start with a sub 0 equals, and then a sub 1, a sub 2, a sub 3, and because we're only doing the first 5, but we started with 0, we'll go to a sub 4. Okay? And this is just like evaluating expressions. So 2 raised to the 0 power over 0 factorial. Now this is defined because remember 0 factorial is 1. And 2 raised to the 0 power is 1, so this equals 1. Quite simple. And then this would be 2 raised to the first power over 1 factorial, which we also know is 1. So it simplifies to 2. And then a sub 2 is 2 raised to the second power over 2 factorial, which we've got 4 over 2 times 1. They cancel, and we're left with 2. The next one is a sub 3, so we say 2, wait a minute, sorry, I changed my pen. 2 raised to the third power over 3 factorial, which is 8 over 3 times 2 times 1. Well, you have 8/6, which reduces to 4/3, or 1 1/3. And then the last one, the fifth term, would be 2 to the 4th over 4 factorial, which we know is, I'm just going to say right here, this is another way to simplify it, 4, 3, 2, 1. Well, and again, you don't have to show this 1. Even though I've been doing it, you don't have to show it. Those cancel. These 2 cancel with this one, so we're just left with 2/3. That's another way to simplify your answers before you write them out. You can obviously delete or cancel out common factors before you finish multiplying everything. It just makes it easier, just like you did in pre-algebra and algebra and algebra 2. So let's look at example 6 to evaluate each factorial expression, or basically simplify each factorial expression. Let's do these together, then I'm going to give you a couple of other ones to practice. They are not in your book for you to practice on your own, and then we'll come back and do them together. So for this first one, we could write out 8 times 7 times 6 times 5 times 4. We could do that pretty simply, but it takes time and it takes a lot of effort. But what we could do instead is I could write this numerator, 8 factorial is 8 times 7 times, I could just rewrite this as 6 factorial, because it's the same thing as saying 6 times 5 times 4 times 3 times 2 times 1. And again, I don't have to show the 1. 2 factorial is just 2 times 1, so I'm going to write that as 2. And I'm going to leave 6 factorial the way it is. So now you can see that these are the same. They're common factors. They can just be completely canceled out. And then 2 has a common factor with 8. It's 4. So now I'm left with 4 times 7, which ends up being 28. So see how simple that is to simplify a factorial expression. Let's do the next one now. 2 factorial times 6 factorial. Well, 2 factorial, I'm going to leave it the way it is, which I could leave it as 2 factorial or I could just leave it as 2. It doesn't really matter because 2 factorial is 2. And then 6, I'm going to go 6 times, because I have a 5 factorial on the denominator, I'm just going to leave that as 5 factorial. And then we have 3 times, again, 2 factorial times 5 factorial. So do you see how I can simplify common factorials easily by leaving them in factorial form instead of having to write everything out? And then 3 goes into itself once, it goes into 6 2 times. So this expression simplifies down to the number 2. Now this last one's a little different because we're dealing with variables. I do want you to look on page 559 in your book and see how they solve it. They solve it by multiplying 1 times 2 times 3 times ... times n minus 1 times n for the numerator. They expand it. And then they expand the denominator the same way. 1 times 2 times 3 times ... to all the way to n minus 1. The thing is all those 1, 2s, 3s, everything that you, as far as you go, it doesn't matter how far you go, they cancel each other out. So I'm going to go backwards just like I've been going backwards with the other problems. And I'm going to start with the numerator. It is n, and then the number below it, the term before it, would be n minus 1, wouldn't it? Right? And I could keep going with that. N minus 2, n minus 3, but I don't need to because I have an n minus 1 on the denominator. An n minus 1 factorial on the denominator. Just like that. I have to put the factorial here because it does continue. It goes on forever and ever. But I have an n minus 1 factorial on the denominator as well. So that would just cancel with that, and I'm simply left with an n. Okay, if you didn't see how that worked, stop, rewind the video, watch again. Look on page 559 at example 6c. See how they simplify it. You can do it that way. It's just a little more effort, but it's the same as if you use the commutative property and multiply backwards instead and simplify the way I've been showing you how to do it on this example. So now I'm going to write up 3 more examples that I would like for you to pause the video and try them on your own, and then come back and we'll look at them together. Actually, before I write up the problems, I'm going to, I wrote up a reminder. Remember that factorials follow the same conventions for order of operations as do exponents. So for example, like we looked at in class, 2n factorial, when you don't have parentheses around anything, it's saying 2 times n factorial, or 2 times 1 times 2 times 3 times 4, all the way to n. But if you have parentheses around it, then the whole thing is a factorial. So it's 1 times 2 times 3 times 4, all the way to 2n. Remember that when you're simplifying the next few problems. Okay, here are 3 more problems. I'd like you to go ahead and look at them, write them down, pause the video, and try to simplify them. And then come back after you've done to see if we have done it, if you've done it the same way I have. Okay, we're back. Let's look at the first green one here. I hope you can see my cursor. So we started with 2n plus 2 factorial over 2n plus 4 factorial. Now the bottom, the denominator, is larger than the numerator because we've got a plus 4 here instead of a plus 2. So that's the one I'm going to deal with breaking down. I'm going to leave the numerator the way it is. These examples and the ones that we did before it show why it's easier to go backwards instead of counting up to count down with the factorials when you're simplifying. So I'm going to start with this 2n plus 4, and I'm going to rewrite it as 2n plus 4 times, well, it would be multiplied by the next smaller number, which would be 2n plus 4 minus 1, because I just stepped down by 1 integer each time. So, and then the next one would be 2n plus 4 minus 2. And I'm going to stop there. I'm going to make it factorial. I could keep going. I could say 2n plus 4 minus 3, 2n plus 4 minus 4. Multiply all of those terms together, but I don't need to do that, or all those factors together, but I don't need to do that because 2n plus 4 minus 1 simplifies to this 3. You see I've underlined them both in purple, but the 2n plus 4 minus 2 simplifies to 2n plus 2 factorial, which is the same as the numerator. So that means that I can cancel this factor with this factor, and I'm left with a 1 on the numerator and a 2n plus 4 times 2n plus 3 on the denominator. Now let's look at the blue one. We've got 2 times n factorial over n factorial. Well, I just rewrote it as 2 times n factorial. I just put a multiplication sign in between the two. I could keep going down. I could say n minus 1, n minus 2, n minus 3, but that would be the same as the denominator, saying n times n minus 1 times n minus 2 times n minus 3. I don't need to do that because I see that I have common factors of, I don't know what just happened there, but n factorial and n factorial. So when I simplify them out, I'm left with just a 2. And that would be the second problem simplified. Now let's look at the last one, the purple one. We have 2n plus 1 factorial over 2n factorial, the whole thing. The numerator is greater than the denominator, so I'm going to be working with that one, simplifying that one. So I rewrote the first term as 2n plus 1 times 2n plus 1 minus 1, and I could keep going to 1 minus 2, 1 minus 3, whatever. I could go down to infinity, but I don't need to, because 2n plus 1 minus 1 simplifies, as you can see from this blue line here to this one, just to 2n factorial. And because this is the same factor as that, I can simplify them. I can cancel them out, and I can simplify this as 2n plus 1. So look over these, take a moment, look these over, see what you did, see compared to what I did, and think about it. Look over the examples that we did before again, and make sure that you understand it. Or rather, I should say understand how to simplify factorials. Maroon. Remember that word, maroon. Okay, now let's look at what we can do with our sequences. It's useful to have 2u sequences, but it's also useful, or even more useful, to figure out the sum of sequences, as we'll note in some of our problems that we do, some of our application problems. Now, what I've written up here is what we call summation notation or sigma notation. So what this means is you've got the Greek letter sigma, that's this E looking thing, and then you've got an I equals some number, some positive integer, or a whole number I should say, because you can start with 0, all the way up to n, where I is your index of summation, and you don't have to use the letter I. You can use the letter K. They often do. You can use other letters. 1 is in this case, is the lower limit of summation, but it doesn't have to be a 1. It can be any whole number. And n is your upper limit of summation, and it can be any positive integer up to infinity. But anyway, we're not finished with the definition here. Basically, this sigma notation or the summation notation it's saying that you need to add the terms of a sequence. So sigma a sub I, your sequence a sub I, is the same thing as saying the first term plus the second term plus the third term plus the fourth term, and so on until you get to the last term, a sub n. I should put a plus there. So this right here that I'm putting a box around is definition of summation notation. It's also been called sigma notation. And we're going to look at the example 7 on page 560 to see how it works. So what this summation notation right here, sigma from 1 to 5 of 3i, what that's saying is what is the sum of the terms from the first 5 terms, the first term, second term, third term, fourth term, and fifth term of the sequence defined by 3 times I. So all you would do is you would say 3 times 1, that gives you the first term, and then you're going to add 3 times 2, that gives you the second term, plus 3 times 3 for the third term, plus 3 times 4 for the fifth term, plus 3, or for the fourth term, sorry, times 5 for the fifth term. And then you would simplify it any way that you want. You could factor out the 3, add the numbers together, then multiply by 3, or you can multiply each one of the numbers by 3 and then add them together. It doesn't matter how you solve it. When you solve it, this simplifies down to the number 45. And that's how summation notation works. I would like for you to pause the video and study examples B and C on page 560 for a moment, just as a review to see how, see some more examples of how summation notation works. If you want, you could also just figure it out or solve it out yourself and then check your answers with B and C. It's up to you, but just take a few minutes to do that. Okay, I pasted the blue box from the top of page 561 in your book onto this video so we can look at the properties of sums. So for example, the first one right here where it says the sum of C, where C is a constant, is just the constant times the number of terms. So for example, if you have the summation of 3 from 1 to 4, that's just the same thing as saying 3 times the upper bound, which is 4, which equals 12. Because basically it's just the first term, which is 3, plus the second term, which is 3, plus the third term, which is 3, plus the fourth term, which is also 3. Or you could just simplify it by saying 3 times 4 is 12. So that's how the first property works. The second property tells us that if you've got a constant times some definition, or a constant times some function, you could move the constant outside of sigma and solve the summation of the series of the sequence, and then you could come back and multiply it by that constant. I wrote up an example. You could do this as 4 times 2 times 1 plus 4 times 2 times 2 plus 4 times 2 times 3 and solve it that way, or you could solve it as 4 times the whole sum, 1 to 3 of 2n, which would equal 2 times 1 plus 2 times 2 plus 2 times, 2 times 3, and then you take the whole summation and multiply it by 4. So when we solve it the first way, we would say 2 times 1 is 2, times 4 is 8, 2 times 2 is 4, times 4 is 16, and 2 times 3 is 6, times 4 is 24, and then you would add 8 plus 16 to get 48. Or you could say 4 times 2 times 1 is 2, plus 4, plus 6, which gives you 12. So it's 4 times 12, which also equals 48. Sorry about this being so sloppy, but do you see how this property works? You can move a constant to the outside of the sum and multiply at the end. I'm not going to do examples of properties 3 and 4, but basically that's saying is if you've got two functions that you can add together, you can take the summation of them added together first, or you can separate them into two different terms, two different sums. Or same thing if they're subtracted on property 4. You can subtract the functions first and then take the summation, or you can take the summation of each one and then subtract them at the end. So now we're going to get to the last part of this section, which defines what a series is. And a mathematical series is simply the sum of the terms of a finite or an infinite sequence. That's all. You learned in class that a sequence is just a list with ordered members, a first member, a second member, a third member. It's a list of numbers. Or mathematically, it's a function whose domain is the set of all the positive integers. Then we learned that the sum, it's more useful to often find the sum of the terms of a series, of a sequence. And now we're learning that that definition is actually a series. A series, again, is just the total or the sum of the first n terms of a sequence of a finite series, or it's adding all of the terms together of an infinite series. Up here you can see in the definition, this is also on page 561 in your book, how the definition works. The number 1 says the sum of the first n terms of a sequence is called a finite series, or the partial sum of the sequence, and it's denoted by first term plus the second term plus the third term, all the way to the nth term of a sequence, which is really equivalent to just the summation notation, or the sum of all those terms. The sum of the terms of an infinite sequence in part 2 is called an infinite series, and it's denoted by the same thing, only instead of having at the top your upper limit is being n, your upper limit is infinity. That's it. So let's see how this works by looking at example 8. If we've got this series of from 1 to infinity, or the infinite series of 3 over 10 to the I, part A says find the third partial sum of this series, or this infinite series. So basically, all you're going to do is rewrite your series. Instead of going from 1 to infinity, we're going to go from 1 to 3, because it says to find the third partial sum. And then we're going to find that sum by substituting 1, 2, and 3 in for I. In other words, we're going to find the first 3 terms of the series and add them together, or the sequence and add them together. Oops, I put the wrong number up there. Hold on. Just a second. I meant to make that 1. Sorry. So 3 over 10 to the 1 plus 3 over 10 to the 2 plus 3 over 10 to the 3. And when I solve that, that's the same thing as saying 3 over 10. Oh, sorry, that's a 3. 3/10 plus 3 over 100 plus 3 over 1,000. Now, it's really easier to solve these not as fractions but as decimals. So this is the same as saying 3/10 plus 3/100 plus 3,000, which when you add it together, it's 0.333. And then part B says to find the sum of the infinite series. So you would do the same thing, only you would have to keep going. So we would add 3 over 10, 3 over 100, 3 over 1,000, 3 over 10,000, 3 over 100,000, and so forth. And you would get the same type of answer, only it would go to infinity, because we're going to infinity. And you've learned that 0.333 going on to infinity is the same thing as saying 1/3. So the sum of this infinite series is equal to 1/3 when you add all of its terms together. So now I would like for you to try this example on your own. It's not in your book, but just find the sum of this series that's defined by -1 to the k times 2 times k, where k goes from 1 to 4. So go ahead and find the sum of this by pausing the video, working it out, then coming back to see if you've done what I've done. All right, see if you worked it the same way I did. You may not have moved the 2 out. Right here, this, I don't know if you can see my cursor here, but this 2, I moved the constant 2 right here. I moved it to the outside of the sigma, used smaller numbers, and then multiplied by 2 at the end. You do not have to do that. You can keep the 2 inside and solve it with that inside. But your answer, when you solve it simplified down, should be 4. Take a second to study what I did, compare it to what you did. Hopefully we got the same answer. Example 9 on page 562 of your book is an application problem. I would like for you to study that, make sure you understand it, and then you can go ahead and do your homework. At the top of your homework page, I want you to write that you watched the video, that you studied example 9 on your own, and you can write the word that I told you to remember at the top of your page. And I will give you points for that for your homework. Have a great day.